So I think I hear the Yi.
Yeah, may I ask you a few?
So Yi, go ahead.
Thank you, Professor Massimo Ruzzene. A long time no see. Thanks for this talk. So I have two questions. So the first one is, can you please go back to slide maybe 31 or 32? In that slide, you show the Fourier form transformed amplitude.
This one, or?
For the shear wave, I think.
Yeah.
Yes, for shear wave. So if I say the last figure for the last column, the Fourier form transformed amplitude looks like there are two isolated rings, right?
Yeah, yeah.
So for one, the rings have a smaller wave numbers, other has a larger wave numbers. So that looks quite different compared to the longitudinal wave case.
Yeah.
If shear wave case seems for a single.
I agree with you. I don't know why. I think we're looking at this. So I agree with you. I have similar questions that you have. So we've observed this. I would say the only thing that I could say is, like I mentioned, exciting a omnidirectional shear is very hard, right? To excite it in an omnidirectional way. So yes. I'm wondering how much it's the effect of the excitation and how much is the effect of the geometry. But there does need to seem to be a underlying scale into the wave field, which we're trying to understand. Our homogenization only captures the lower one, right? You can see the circle.
Yes.
But I have similar questions as you have, so I don't have a good answer for this. So
yeah, I just have maybe a very naive guess. Perhaps you can plot the band structure and you can show that there are two solutions corresponding to one single frequencies for a specific direction. Simply band structures.
Yeah, the problem is the band structure for these. I don't know how to do it. We could do it for a large domain and apply periodicity conditions. But if you have ideas how to do it for these domains, it could be interesting. We can certainly do it for the 4-fold and 6-fold, and we can look at those. But they don't seem very peculiar as much as these ones are. So
yes, the problem in how large the domain is. I think if you just choose a small domains, the band calculation can be just as easy as for periodic structures.
Yeah.
So in addition, this domains contains quite large.
So we have an underlying KR, which is the underlying length scale, right? So we have the circle in our design, and we use that, and then that defines sort of an equivalent period, and then we try to make it maybe 5 or 10 periods like these domains. The problem is we make them wide. We have a very, very messy structure, and it's very hard to see and understand anything from those because we have so many branches that cross and so on that it becomes very complicated to observe. If we make it very small, it becomes clean, but it's probably not very representative of what really happens. So we've been struggling with this a little bit for some time to really come up with band diagrams that are useful for us to understand the behavior. So I'm happy to talk more about this, and maybe if you want to have if you have some ideas on how to do it, I'm happy to listen. But then we switched to the wedge type approach for now. So,
yes. My second concern is that you just partially answered my second question already. So my concern is that you observe this isotropic effect for 8 and 10 and 14-fold symmetries. I think this kind of isotropy is only observed because you choose a sufficiently large square domain, right? If you choose a smaller domains, the 4-fold symmetry of the lattice. still preserve, and that will still give you more or less a isotropic result.
Yeah, I think there are two critical parameters. One is the size of the domain, and one is the frequency that you do. So I think so. The square lattice.
So perhaps only for the static case. For the static case, yes.
Yeah, for the static case, even the square lattice is depending on the volume fraction, but it's already anisotropic, even in the static case, as shown by these. Maybe I can go back.
So it's already become clearly isotropic when the domain is about how many periods?
So this is a homogenized Young's modulus for the square lattice. So yes. You would expect, if we done the homogenization right, which I think we did, is you can see that it's non-isotropic, right? And then if you do a wave propagation, or you do the isofrequency contours, even a very low frequency, you should see a very similar pattern, angular pattern.
Yes, yes.
Okay. Then increasing the frequency will only, if you go in the frequency dynamic domain, it will only make it worse in terms of isotropic. So as you increase the frequency, you will see more and more directionality in these designs.
And for the quasi-periodic case, 8-fold case, you get an isotropic result when the period in this domain is about 5 or 4 times larger than the period. Right?
Yeah, I think so.
So
this is
if you still you go to a smaller these domains, so the result will become more or less isotropy, right?
Yeah, I think so. I think the purpose here is to see what the equivalent properties of a system are and the equivalent behavior of the system are. So as a composite. So if you go very low in a very small domain, then you can no longer treat it as a composite, right? Because the two phases are very important and they cannot mix very well if it's very, very small.
Yes, yes. Because I was interested in these questions, when we studied the three-dimensional quasi-periodic lattice.
Yeah. So
in our case, for the 5/3 approximations, the lattice constant of this cubic unit cells is also about maybe 7 times larger than the smallest we can call characteristic lengths and the structures. So it's more close to isotropic. So I was just wondering, so for this two-dimensional case, at least how large this domain need to be to get a nearly isotropic result?
Yeah, again, I don't know that we have answered the question. I think what we did is we wanted to get a large enough domain that we could get convergent results in terms of the equivalent properties.
Yes,
I don't think we have asked the question of that you're asking me. So we haven't really investigated this.
Okay, thanks.
Thank you.
Okay, thanks. Any other question? Check at the same time if in the chat we have anything. No. So I have a naive question regarding your slide 36 or 37. So it's just
this one.
Yes. So basically here you apply like block conditions along the radial direction on this you call cyclic boundary conditions. And what do you use as boundary in the radial direction?
We let it free. You can choose, but we let it free.
Okay, you let it free. Okay, the question was actually related to the lower right panel where you have this mode, this bit weird mode excited actually on the edge. Okay, yeah. But then if you leave it free, okay.
Yeah, yeah. And I think you would probably see not much change in terms of the bulk, so the dark areas, but you'll see maybe changes in the spectral content in the low density states region. So these modes will not be there, obviously. Okay. And yeah.
Okay, thanks.
Thank you.
I've got a Another question regarding this slide. What happens if you move to clamped condition instead of stress-free?
At the end, at the edges, right? At the radial edges?
Yeah. Do you preserve the defect modes or would they disappear?
They would, these ones at the edges would probably disappear. I think this one, I don't know that I want to call it the defect mode. It's clearly a strongly localized mode. And we have a number of them. Those will persist. So.
Yeah.
Because you see here, in fact, I totally agree with your model regarding the block condition for this sector, but I don't know if this block spectrum converges to the block spectrum of your quasicrystal. I'm not sure about that. You might treat a different problem here.
Yeah, I agree with you. I think it's a truncated system radially, so we made some.
And you know, you gave an answer which is not very encouraging, because if you want this to converge to the block spectrum of the infinite sector, then these modes should not change at all if you change stress-free to clamped or to other condition. If it is very sensitive to this condition, this means that you treat a totally different spectral problem.
Yeah, I agree. I think if you have thoughts on how to get the infinite system, so here we try to make it fairly large that we can do it computationally. But the truncation will introduce changes, and I think opens the question of whether we've converged to the infinite system in the radial direction or not. I agree with you.
I think the absolute expert is Yi Chen actually on these questions, but it's very, very interesting, your graph of the density of state. So what you say is that the density of state is very, very low for your defect mode. The defect mode you show, this is what, is it true for the mode which is located near the stress-free? Maybe I have misunderstood what you said.
So the density of states is plotted as the delta omega divided by delta n, where n is the mode order. And so we plot it, and then we assign a color to each of the modes. And,
but for the defect mode, it's very low, no? For the defect mode, it's almost white.
Yes, so it means it's an isolated mode. So it's for sort of there's no modes next to it, and it makes us think that we're inside the gap, like if you were in a periodic system where you truncate the system, and then you have defect modes. So the density of states there is also very low, and then you have a defect mode there. So the behavior we observe is sort of consistent with this analysis.
But then, if your sector, let us imagine that you take the limit when your sector becomes infinitely long, the density of this defect mode would be totally zero?
In theory, it should go to zero, right? You should have a gap that cleans up and becomes zero, in theory, yeah.
So really, to check if your approach is correct, that's the convergence of the density of state of this mode that would give you the answer. You know, when you enlarge the sector, it would be some kind of numerical proof of the convergence of your spectrum towards the spectrum of the real quasicrystal, perhaps.
Yeah, that is true. I think that is correct.
I did not know this. It's really beautiful, this cyclic boundary condition. I did not know. So who worked on this kind of cyclic boundary conditions before?
Yeah, so there's we looked at several papers. I think it's very well established in turbo machinery. So where we have the disks and they have large finite element models, and they have to get the modes, and then they only do a wedge, and then they apply the boundary conditions. And then obviously in the angular range is a finite system, so you have to go back to the original value. So you only have finite discrete values of n that you can do, as opposed to a translational symmetric one where you can change the propagation constant in a continuous way, but here you have only discrete values. So there's a paper by Thomas in 1973, and but I think it's fairly established technique, I would say, in the turbo machinery, for example.
But was it used before in the context of quasicrystals to look at their spectrum?
I don't know. I'm not sure.
I haven't seen it.
I've never seen it. But may I just ask regarding this, let's call it cyclic boundary conditions. So I totally agree in this machinery. And when you have this kind of machine, basically, the reason why you use this cyclic boundary conditions. But here it's a bit weird because your system is not, it's not like a finite in the space. You don't have something cyclic and you don't consider anything like outside. If you would not assume integers here like this n over n in your, but if you would assume something continuous, then you would get a continuous dispersion relation here, this omega versus n. It's a bit weird, but let me take a book just to try to explain. Basically, instead of considering that the mode has to cycle around, you could say that basically it's starting here, it's rotating, and then it's just rotating under another plane. The reason why I'm saying this is maybe more close to the infinite case of the crystal, because you will find again this the periodicity in the next neighbor in all directions. So here you have fivefold symmetry, and then you will mimic more, maybe more accurately, the infinite case of this perfect quasiperiodic structure.
I think there's other ways. I definitely would like to talk about it. I think to us, they are rotationally symmetric. So you can identify a wedge and you can rotate it this way, for sure. So that's why we use this technique. But there may be a better way to explore the space in the reciprocal space than what we have done. So if you have ideas, I think this was our first attempt, and we got some indications of these gaps, and by using the density of states. So that's where we went with it. I'm not saying that this is the only way, but yeah.
Okay, thanks. Any other question?
I have one
Emil?
question. First, I would like to make a comment about these pizza slices. We just have a group of finite rotations, which is an abelian group, and what Massimo does, he just organizes the eigenmodes by representations of this group, and this is how this block type boundary conditions with respect to the angle come about. So I think what he does, it's very clear to understand. But my question is, and maybe to open a discussion, you have this very nice way of generating these patterns. And so far you are careful to put these points symmetric on the circle. I think if you relax this condition and you have one parameter in which you relax that condition just using one parameter, then you can plot the spectrum, or at least the density of states, as a function of this parameter. And I'm sure that Hofstad butterflies will start to appear. And in that case, it will be much easier to understand and to actually identify the gaps in this system. So it's always when you have a system and you plot one spectrum, then you have limited ways to assess the gaps. But if you have one parameter and you plot the spectrum as a function of one parameter, then you start to see features in the density of states. So that could be an interesting path to explore.
Yeah, no, I agree. We have been thinking about what parameter to change because, as you know, Emil, we've been working. We need to be exploring butterfly spectral properties, but we have not found a good parameter to use. To be honest, and I'm not saying that there isn't one. I'm just outlining and and making clear what our limitations have been so far. So if somebody has good ideas, I'm happy to discuss and say, maybe, yeah, we tried this before, or if you have, I'm sure people have better ideas than we've had so far. So.
Yes, in one dimension, if one starts with 2 points and the 2 points are on the circle, just making 1 point be outside of the circle and these vectors being uncommensurate, you already starts to see Hofstadter butterfly. So just making one of the vectors incommensurate with the others is a start.
Emil, I have a question. So for you, the block spectrum computed by Massimo is indeed the block spectrum of the real quasicrystal?
Yeah, provided in the radial direction, it goes all the way to infinity. So what I was saying, it's only about the angular boundary conditions.
But really, this radial,
the pizza slicing is nothing but organizing the eigenmodes by irreducible representation of this tenfold rotational group.
And so, in essence, your block spectrum is only aware of the periodicity in the azimuthal direction. This is, in fact, it's like having a one-dimensional problem. This is what.
So, yes, but then you have many degrees of freedom which still remain from the radial dimension. So it's a one-dimensional system, but with a large number of degrees of freedom. So you have many bands which you still have to account for. So this is only one way to organize the modes.
Yeah, I agree that for one n, any n value, it's a one that is effectively a one-dimensional system. But in our case, it's truncated. So, Sebastian, I don't know if you have an idea about how to make it longer or make it converge. If there's any theoretical framework to use to say that if we make it large enough, and what that's large enough is computationally, so that we are close to sort of approximating the limit.
Because, Emil, are you aware of some people who have actually computed such block spectrums? Are you aware of some people who have really computed the block spectrums of, two-dimensional quasicrystals, but in a very, rigorous way, not supercell or, I'm not aware of any work.
So Jean Belizard, together with Beku Siegfried, they started a program on periodic approximants of aperiodic patterns.
Yeah.
So they put out 2 papers on how to approximate quasicrystals by periodic approximants so that the spectrum, in fact, converges. So then you can wrap it up in a periodic, into a structure without edges, and then the statement is that as you take the size of this wrap-up system, then the spectrum converges to the real spectrum. And they have statements about 1D and 2D quasicrystals.
I know some of their papers, but they were working in the context of the Schrödinger equation. No? It was some kind of, I don't think, yeah. I'm thinking of some papers of the 80s, actually, some old papers.
Oh, these are quite recently. So I think the last paper was in 2019. And another result is if you look at the density of states of such a system, then there is a rigorous proof that as you take the edge, so wedges with open boundary conditions or any, if you take the edge further and further away, then the density of states converges to the infinite case.
Okay, I was not aware of this.
So that's a good news, but
so, and this depends also on the order, well, of course, on the order of the rational approximant. Because we have this problem that for a quasicrystal, you know, they are linked to the golden number, and the rate of convergence of rational approximants to the golden number, it's a very slow rate. So maybe you need to take a super large cell until you reach, you know, convergence. Perhaps that's the issue, you know.
Yes. So one way to approximate, for example, in this cut and project method, the cut and project method uses a square window or a window with corners, and one way to approximate it is just to round up that window and then take the window towards the limit where you have sharp edges. So that's doesn't involve rational approximants or
I feel more comfortable with this cut and projection approach because you have periodicity there, so you can apply Bloch's theorem and so on, you know. But then, of course, when you cut project, people are trying, you know, the two approach, either very large supercells or either taking the higher dimensional space, computing the Bloch spectrum, and then cut projecting the spectrum onto 2D or 3D. But there was some kind of work from the group of Stephen Johnson, but I haven't seen any convincing paper so far. So perhaps,
I could, yes.
People don't seem to be able to give the true, you know, Bloch spectrum because there is this kind of self-similar feature of the spectrum. It's, you know, it's like a fractal, this set as well. That's really an issue because, you know, in fact, when you take larger and larger cells, you can see more and more gaps appearing. So when do you stop? You know?
Yes, in fact, just for the one-dimensional quasicrystals, the statement is very interesting. If you have the parameter which is commensurability, which you vary continuously, then the spectrum is continuous at any irrational number, and the discontinuities appear at rational numbers.
Okay. So at least you say that the problem is solved in 1D, in the 1D quasicrystal self.
And also the 2D, I think there are clear statements about how to get periodic approximants which convert, then their spectrum converging to the real spectrum.
Okay, I wasn't aware of that. Okay.
In the 1D case, it's relatively easy computationally to extend the spectrum and keep extending it until you see convergence. And I think one of the challenges in 2D, and in this case, is also that at some point, computations become very challenging to run. So that's an area, I think, to me, that it's quite open, you know, because it has computational challenges. I think the brute force is extending and then show convergence. But the challenge is to know from a theoretical point of view when to stop, when you can stop.
Yes.
I think Sebastian was mentioned as well.
At least looking at the density of states, that's a sure bet, and which is what you are actually looking at in this graph to the right. So I think there is no spurious effects there.
Okay, thanks, Emile and Sebastian, for comments. On the chat, we have a question from Fabrizio, and I will just read the question for everyone. At the very beginning of the dispersion section, you plotted the modes in the dispersion curve evaluated by block analysis. I expected to see symmetry around the zero wave number, as it happens for periodic lattice. Is this caused by the fact that the lattice is quasi-periodic?
Yeah, I'm not sure which one is referenced there.
He's just writing at the beginning of the dispersion section. So, very. Fabrizio, if you can take your microphone, or if you can write more about the question.
Is this a reference to this case or
the other slide, isn't it?
I think in the beginning.
I wonder if this is the one.
It was the first slide when you introduced dispersion characteristic.
Okay, I'm not sure. So this is the slide or?
That one.
This one, number 29?
That one. Thank you. Yes,
okay.
Yes, apparently.
So the symmetry, I'm not sure which symmetry you're referring to. I think
well, I believe that he would like to see in the symmetry in the gamma x and gamma minus x, let's say, direction, but this is not common to plot, I would say, in our field.
Yeah, this is m gamma, so it's a 45-degree direction. So I'm not sure if that's the question. It's a triangular reducible zone that we've used in this case. So it's not going to be the same in between gamma and x and m and gamma. I don't know if that is the question. He says it. He got it. Thank you. So
thank you.
I have a question regarding, so you apply the Helmholtz decomposition, so okay, but the Helmholtz decomposition, you can apply it because here you have just one material, no?
No, we just do it numerically from the results. We take the divergence and the gradient of the data, and in the numerical from the numerical data. So
because usually you can only apply the Helmholtz decomposition in the Navier equation when it is a homogeneous material, no?
Yeah. No, I think we don't do it in the solution process. We numerically simulate the response, and then from the displacement components, we evaluate the divergence and I don't know how to say, the rotation here, and then we do it numerically. So once you take the ux and uy component and you compute these finite differences, you decompose the two modes, you separate the two modes. So you only see, it's not a Helmholtz decomposition in terms of potentials that you do it in the solution process, but we do in the post-processing phase. So we can separate the two modes from the numerical solution and visualize only one and the other.
Because here the Helmholtz decomposition theorem would not be true, since it's not.
No, you're right. We just use the same operation and apply the same numerical operator to the solution, to the numerical solution.
So did you try to just excite the P wave or S wave independently? In that case, you don't need to take the divergence or the curve of the displacement field.
Yeah, we can try. I think we don't find it necessarily too easy sometimes. So We use this in experiments as well, when we did some experiments in the past, and we found it efficient, so we just went this way. And there's also the option of imposing a pure mode in the simulations, that's for sure.
Well, I'm not sure this helps or not. Sometimes when we do numerical calculations, we excite the P waves just by cutting a hole in the structures and expanding the holes or rotating the hole to excite a P wave or S wave independently.
I know that is a good suggestion.
I'm not sure that helps or not.
Yeah, no, that is a good suggestion. We just had this tool that we had developed for experiments, and we used it in this case as a post-processing.
I think your post-processing, I mean, this decomposition is it's very valid until basically your wavelength in the system gets on the same order than your inclusions.
Oh yeah, of course. Yeah. So
and
this
here, as you are in the long wavelength, it should be fine.
Yeah.
But you've got to be extremely careful because the Helmholtz decomposition, well, this theorem, clearly you need an isotropic homogeneous medium. And here, even if it treats this as an effective medium, the effective medium is still anisotropic. So, you know, this decoupling is, I understand, but it's...
Yes, but she's just applying it on the solution directly. And the solution does not really see this the underlying material anymore.
Yeah. Yeah.
But it sees the anisotropy. It sees the anisotropy.
Yeah, but it's very weak compared to the to the material itself, to this inhomogeneity of the material.
Agree.
And also, I'm very sorry because I'm asking very obvious question, but here, so this is the plot for a quasicrystal?
This is a fourfold symmetric, so it's a square lattice.
Lattice.
Okay, that's all it is. Okay, all right.
Yeah. Two materials here. Did you try to calculate the individual shear wave for these two materials?
Okay.
Well, that these two seems isolated rings are corresponding to the two shear wave mode in the materials.
I didn't catch the last part. Sorry.
Because you have a bimaterial here, and this two material has two different shear wave velocities. Not sure these two seems isolated rings part comes from the two shear wave in the material because they have different wave velocities, and the corresponding wave number should also be different. So that's why you get two rims have different wave numbers at the same frequency.
Yeah, perhaps that's true. That is correct. Maybe as we go higher in frequency, this becomes more evident.
Yes, perhaps.
Yes, because for a given frequency, for the P waves, you are probably more in the homogenization domain than for the S waves.
Yeah, this is still very linear dispersion in this range, as you can see. So, yeah, I agree that as you go in frequency, this decomposition will create spurious modes, perhaps because of the way it's calculated. So maybe that's the reason for these additional rings that you mentioned before. Yeah.
Yeah. So yes, it was the point. Maybe what you see are just the artificial features of your decomposition.
I agree. Yeah, that is a good point.
Is there any other question from the audience?
I have a question. Maybe I can just ask a very quick question. So this is a Pi here.
Yes. Hi,
how are you?
Good. Thanks for the presentation. So my question is really, you've been talking about the design method, which is rotational symmetry, and you got that from the reciprocal space. And your analysis method includes multiple things that you did. So I'm wondering whether any of those are applicable to more amorphous media, in the sense that for something that without rotational or exact rotational symmetry, will any of the method we can still use?
It depends on what methods you refer to. In terms of homogenization methods, we apply the technique that I think it works for random media, as long as you accept the limitation of the choice of RVE that you make. So that is the main question and the main assumption, right? So you have to choose some sort of RVE that it's really an R representative, and that is the key question there. So if it's you could also try to see and break the rotational symmetry in this design process, because we chose to make them, as Emil pointed out, we chose to make them on the same circle, which enforces rotational symmetry and they're evenly distributed. But one can play around and see what happens when you don't do that. You can just assign these delta functions in some very strange way, as you wish, and then see what you get, and then analyze them. So obviously, if you don't have rotational symmetry, you cannot use the wedge type approach that we used. So you would have to use some other methodology if you want to estimate the spectral properties. So,
okay, got it. Thank you very much.
Yeah, hopefully that explains.
Emil, you have another question?
I'm not sure. Do we still have time, or it's way
until the speaker, I mean, as long as the speaker is here, you can always ask questions.
So the way the patterns are designed, you can, because it's just an independent sum of terms, can they be thought as overlaying the periodic patterns on top of each other? Maybe even SMOR pattern?
Maybe, yeah, that is a good point. So you could do maybe individual block analysis on all of them, but then you'd have to find a way to combine them, right, to see what kind of information you get.
So what I'm saying is, if in your design you take two vectors, let's say, and another for 4 points, and you plot them in different planes, what do you get? You get periodic structures, which maybe they are a little bit rotated. And then as you bring them down, you actually get your quasicrystal. So,
yeah, I think that's a good way to see it. And again, you have to see, I don't know if there's any interaction. Obviously, it's a linear superposition. So as long as you can enforce linearity throughout the process and the superposition principle holds, maybe you can, you can see it that way.
Okay, thanks. Is there, let's say, a last question if someone has one? If not, maybe let's thank Professor Ruzzene again for this very nice talk and for almost half an hour more of questions.
Oh, thank you very much for all the suggestions. I think it gave me a lot of things to think about. I think this is great.
Thank you for the presentation and for your time.
All right. No, thank you guys for organizing this and giving me the opportunity to interact with this great community.
You're welcome. And it's, I mean, we hold these seminars every week, so I think it's a good opportunity to on this on the mechanical metamaterials and more generally on metamaterials. And it's a nice place to discuss. We are not limited as usually to like two questions. Sometimes you can get 20. But I think it's a good opportunity because we are not really limited.
Very good.
And next week we'll have Professor Lalande who will give a talk on the same day on Tuesday. So you are all feel free to come and to attend the next seminar. Okay. So thanks very much, and see you next week.
Bye, guys.
Everybody. Bye. Great, everybody. Bye.
Bye-bye.